Hi class, welcome to Refrigeration and Air Conditioning, Lecture 3 on Thermal Comfort. So in previous lecture we looked at food preservation application of refrigeration systems. In this lecture we look at the thermal comfort application. Um, so this is primarily an application of air conditioning systems. Now what exactly is thermal comfort? If you look at the definition, um, it is defined as a mental condition um, of each individual in which they feel satisfied with their respective surrounding thermal environment. So it's a subjective experience. It can vary from person to person, and it's influenced by a multitude of external and personal factors. So the factors that are part of the room in which that person is in, or the environment, and also factors that are directly associated with the person himself or herself. Now, when air conditioning systems are designed, it should be we should be mindful of making sure that they're thermally comfortable for the intended occupants and the number of occupants that will be using that space. For example, in residential, commercial, and industrial spaces. And if there is inadequate planning to address the thermal comfortable levels everywhere within that occupant space, then it can lead to discomfort um, per definition. It could also lead to decreased productivity, especially in a work setting. It could affect health. For example, it could affect sleep and rest. It could also create some safety issues. For example, if you consider the environment to be a lab or a factory, uh, where it is essential to wear proper safety equipment, PPEs, uh, for example, PPEs like a lab coat or a fire retardant coat or a thick glove, helmets, glass, goggles, face masks, things like that. If those are needed for the uh, proper functioning or proper functioning in that lab or the factory space or the workspace, inadequate thermal conditions might lead to the workers not using those safety equipment, which will create a safety issue. So thermal comfort is one of the important considerations when we are designing an air conditioning system. Now let's look into the thermal experience of a human being. Um, so we all know that human beings maintain a body temperature close to 37 degrees C, right? A core temperature. And that's true under most cases for most people, right? Somewhere around this. And we are always losing heat or gaining heat from the surroundings. We're always doing some work and losing some heat that way. So how is our body generating the heat that lets us do all this, right? So there is a metabolic reaction happening within our body, mostly within our digestive system, but also sometimes a lot of energy is released in your muscles and other organs. So overall, you could say there is a metabolic rate in which heat is being produced by the body. Okay, so this is the generation term. And then when you walk, when you move objects, when you climb, when you push things, when you do exercise, you're doing a lot of work. Okay, doing work. When you exchange heat with your environment, you could sometimes be standing in the wind under a fan or a draft. So you're losing heat or gaining heat through convective means. If you walk under the sun or are standing next to a fire, you might be gaining heat through radiative means. The same way you can lose heat through radiative means when you stand next to something that's really cold. When you sweat, you're losing heat through evaporative heat loss, right? In addition to that, each time you breathe, you can see that the air that's going out is full of moisture and it is warm. So you're losing heat during respiration. Okay. So this is the energy balance. So the body needs to constantly adjust your metabolic rate or heat release within your body to make sure that the core temperature stays within a tight control in 37 degrees C. So you have basically a temperature control mechanism in your body. It's in your brain, and it's the hypothalamus, right? That is making sure that your core temperature is uh, is within a tight spec around 37 degrees C. Sometimes your body needs to make sure that the core temperature raises to above 37 to make sure it fights infection. At those times, the hypothalamus regulates the temperature a little bit above, and you develop a fever. Okay, and if the core temperature drops and you're going through uh, hypothermia, or you're exposed to outside temperature and your body is not able to generate or keep up with the metabolic rate, you start shivering. Your muscles start shaking, which is also releasing more heat through your muscles, which is the attempt by your body to raise your temperature. So whenever there is extreme cold, you would have noticed your body tries to shake or shiver. That is to make sure that the energy balance is met, okay, to keep the core temperature high. Now, what are the factors that influence the thermal comfort? So let's look at the environmental factors first. The easiest thing that comes to mind is the temperature of the air next to you. Okay. The next thing is radiant temperature. Okay, so if you're standing in a room temperature air, but if you have a fire um, close by, even though the air is colder, you'll feel warm because of the radiation from the fire. This is the same thing true when you walk outside in a sunny day. Even though the air temperature is within um, your satisfaction, but the moment you come under the sun, you'll feel um, a lot of discomfort due to the radiant temperature. So we have to keep them separate, the air temperature and the radiant temperature. The next is the airflow velocity. So if there is wind or breeze or fan, you feel uh, different. Your perceived temperature of the air seems different. Typically, you'll feel colder than normal for the same air temperature if the air, provided the air temperature is below the body's temperature, right? So convection, this is basically convection. Um, and the last one, the last item from the environmental factor is the humidity. So we will discuss a lot about humidity in the psychrometrics class, but humidity is basically the moisture content in the air. Okay, 100% means that the moisture content is max. 0% means there is no moisture, no water in the air. Now, what are the personal factors? There are two main personal factors. One, how much insulation you have on your body. And primarily insulation is clothing, right? So you could also be carrying bags. You could also be carrying a lot of items close to your body that could contribute to insulation. But in general, it's the type of clothing that you're wearing, okay? And it changes. You have noticed that especially people living in the northern latitudes, in cold countries, they have a different type. They have a different selection of clothing throughout the year, right? They have summer clothing, their spring, they have winter uh, clothing and fall clothing, right? depends on the conditions. So they keep changing the insulation to match the comfort level. In addition to that, the metabolic rate that we just discussed, um, the rate at which the body generates heat, and it's primarily influenced by the activity levels. There are several standards that um, provide guidelines on uh, thermal comfort of a room or a air-conditioned space. And the most important one, or most commonly referenced one, is the ASHRAE 55. Okay, and that is primarily a North American or an American standard, but it's a reference worldwide. Then there's the European standard, energy performance of buildings, ventilation for buildings, that also closely correlate with the ASHRAE 55 in the methodology. The standards themselves may be slightly varying. There's also the ergonomics of the thermal environment, ISO standard, um, energy performance of buildings, indoor environment, and there's another European standard on the energy performance of buildings, addressing indoor air quality, thermal environment, lighting, and acoustics. Okay. Then there are two regional standards or national standards, one for India and one for China. Okay. So in this lecture, we are primarily focusing on the methodology by ASHRAE and the European standard. All right. Now let's look at metabolic rate. Let's figure out some ranges in which the energy is released in our body. So typically there's a unit, specific unit for metabolic rate. Okay, it is the actual unit is watts per meter square, but we also write it in equivalence of METs, metabolic equivalence. Okay, so 1 MET is equal to 58.2 watts per meter square. So it's basically power divided by area, or energy released or generated per second per area. Okay, so that's what the unit is, and 1 MET is 58.2. Where does this 58.2 come from? Apparently, this is the energy that we generate when we are resting. Okay, when we are not doing much work, we are just sitting on a chair. This is the average energy that most people generate. Okay, you can see some empirical results here. So seated quiet is 58.2, 1 MET. Okay, and if you're sleeping, it's lower than how much you would spend when you're sitting. You would have noticed that your sitting heart rate versus your sleeping heart rate is much different, right? So when you're walking, you can almost double it, the amount of energy generated by your body, okay? And when you're really doing strenuous exercise, for example, if you're doing competitive wrestling, you can be doing almost 8 times the energy that you would spend when you're sitting, okay? So what does this mean? If you're doing these activities, your uh, metabolic rate keeps increasing when you do these activities. How does that fit into the energy balance equation? So if you go here, M keeps increasing because W keep increasing, right? And it will consequentially affect these variables a little bit. But primarily the reason why M has to increase is because W is increasing considerably. So if you do a lot of work, you'll burn calories within your body, right? That's the only way to maintain your temperature. If you don't do that, your body will drop in temperature, right? So doing competitive wrestling, for example, would burn your stored food, your fat, whatever energy source is there in your body, it will be converted into energy at 7 times to 8 times the rate in which it converts when you're seated quiet. Okay, and these are per ASHRAE 55 standard. These are some empirical values that are defined in ASHRAE 55 standard. Now, how much is the actual energy per second per person? Remember, this is energy per meter square or area, and that area is the surface area. Okay, now we need to find the body surface area of a person to figure out an average energy consumption by that person, right? For figuring out how much heat will be generated by people within a room, we need to know the exact watts, exact power coming out of each person, right? Not the power per meter square. So for this, we can use the Du Bois formula, which is an approximate formula that connects a person's height and weight to that person's body surface area. Okay, so for an average man, the body surface area is, let's say, 1.84 meters square, assuming he weighs 72 kg and the height is 171. And for an average woman, it's also 1.67. Now, if the average man or woman is sitting at rest, you're consuming or you're generating 58.2 watts per meter square, right? So they're basically energy sources that are close to 100 watts. Okay, so sometimes you would have noticed that if you don't have, even if you have a little bit of air conditioning, the more people in the room feels really warm. That's mainly because each of you are generating at least 100 watts within that room, right? Because if you're standing or talking or moving around, you might be generating a little bit more. If your body weight and height are slightly different from this, you might be generating a little bit more. So let's say um, if you're stuck in an elevator with 4 people or 5 people with limited air conditioning, the temperature will raise there too. So it's like running a 500-watt heater in a closed space, right? All right. So the next um, factor is the clothing insulation. How does the standards account for this? So the metabolic rate, we could use some basic standards depending on the type of activity that will be in that room. You could use some of the ASHRAE standards to estimate the amount of heat generated by the activity. Uh, the next question is what type of clothing would be the people or the occupants wearing in that environment, because that has a substantial impact on the thermal comfort. So here also there is a specific unit called CLO units. It's used to represent the thermal resistance per unit area. Okay, um, so thermal resistance per unit area is nothing but, let's say you have a temperature difference T1 and T2, and you have a thermal resistance in between, and it has a thickness T, and this item has a thermal conductivity K. So it's the thermal resistance due to for conduction is primarily defined as T over K. Okay, K is the thermal conductivity as the thermal resistance per unit area. Okay, now CLO, so it's defined in CLO units, but in SI units, the units would be basically um, the units of this item here. Okay, so thickness, the unit is meter. The units of thermal conductivity K is watt per meter Kelvin. So overall, it comes out to meter square per watt Kelvin. Okay. I'm sorry, I think I made a mistake here. So it should be meter divided by watt per meter Kelvin. So the units of this would be meters Kelvin. divided by watt. Okay. So if you're using English units or imperial units, these values would be written in terms of feet, foot square, degree Fahrenheit, hour per BTU. So what is the exact conversion? 1 CLO is 0.155 meter square Kelvin per watts in SI units and 0.88 in imperial units. Okay. Now what does 1 CLO represent? It is the thermal insulation needed to maintain comfort for a sedentary person. That is a person sitting quiet with 1 met, okay, which is 58.2 in a particular environment. So that is 21 degrees C, okay, 70 degree Fahrenheit, 50% relative humidity, and an air velocity of 0.1 meter per second, which is very low. So in this condition, the clothing that is needed to keep that person neutral or feeling satisfied is defined as 1 CLO, and it's been empirically determined to be having an insulation or thermal resistance value of 0.155 or 0.88 depending on the type of units you're using. Now, how does this CLO compare to some of the resistances that you're normally used to? Um, for example, if you have any experience with insulating your house or insulating an equipment um, in your house, you would have noticed this construction material, which is basically an EPS or XPS, extruded or um, extruded polystyrene, um, that is typically represented by an R value for its resistance. Okay, so the smaller the thickness, the smaller the R value, and R value is basically the same as this thickness divided by thermal conductivity. So the thinner the material, the R value would be smaller, right? So it's the same, and the corresponding R value for your clothes when you compare it to um, a construction insulation material like this is 1 CLO is very close to 0.88 R. Okay, so that's another way to make a comparison. How does your cloth compare to a typical insulation material, right? You can compare it by looking at the R value here, and you can see how many shirts, if I wear, would be equivalent to an R value of a typical insulation. Okay, and these R values are in imperial units, by the way. Okay, all right. How are the clothing insulations measured uh, to to figure out the whether the person is thermally comfortable in a particular environment? The way they do that is using two thermal conductivity tests. One is a thermal mannequin testing. Okay, so you create a thermal mannequin which is life-sized, and you have heaters inside the mannequin. Okay, and you also use heat flow sensors. So the mannequin is typically heated somewhere between 35 to 37 degrees C, which is close to the core temperature, right? And it has a control system that tries to control the temperature to this range. Now you change the ambient conditions to make sure um, that the mannequin cools down below this, and then you'll have to adjust the amount of heating needed to match the new temperature. So the difference um, in the amount of heat that is um, needed with and without clothing material under a particular environmental condition is used to determine the CLO value of that particular cloth. Okay. You could also do this without the mannequin, with just a flat heated plate covered by the fabric. Okay, um, but that doesn't fully account for the total surface area of the person. But both these methods are used, and this is how empirically the CLO values for each type of clothing is found out. Okay, this is sort of a heat transfer test um, aimed at making sure that the core temperature is maintained. Now you could measure several individual clothing materials like this. You could also um, measure them as a combination. Okay, so if you might be wearing multiple t-shirts and a socks and trousers, all of them together, right? So these are measured individually. If you're wearing multiple clothes together, um, it is not advisable to just add these CLO values. Okay, if you do that, you're not really accounting for the how the garments are worn together, the chances of air layers that are trapped between them that will provide an additional insulation, things like that. So sometimes approximate formulas are used. ISO 9920 proposes this particular formula. So if you have different clothes with different CLO values, instead of summing them together, you use this particular formula to estimate an average ensemble um, insulation of the whole set of clothes that you're wearing. Okay, so typically this is the value we need overall to understand the thermal comfort within a room. All right, so we looked at the two personal factors that affect thermal comfort. So we looked at the metabolic rate of the occupant and also the clothing of the occupant. Now we look at the environmental factors, and the first one is air temperature. What do you mean by air temperature in this sense? Um, so let's consider the weather forecast. I don't know whether you've ever tuned into weather channels, especially in US. There are several weather channels, local and national level, and they always report the daily average temperature, the max, min, all those temperatures every day, right? Sometimes they predict for weeks and months ahead. So what temperature are they talking about? So when you talk about weather temperature, they're of course talking about the temperature outside your house. But when you walk outside your house, um, the temperature is not the same if you're under a tree directly in a shade, or if you're exposed to sunlight, or if there is rain. Um, the feeling of temperature is different. So what temperature are they measuring and how are they measuring it? What they're measuring is basically dry bulb temperature. Okay, and this will be clear when we talk more about dry bulb and wet bulb in the psychrometrics part of this course. So, um, so this is the temperature of the air in the environment. Okay, so when you're measuring the temperature of air, you, especially if you're measuring it outside of, in our context, we are talking about temperature inside a room. But let's just stay focused on measuring the outside temperature. Because in this case, there is plenty of radiation from the sun. So that radiation has to be shielded. So they use shielded ambient sensors, air sensors, that shield from sun's radiation, uh, the direct sunlight from reaching the temperature sensor inside. In this case, you can see the sensor here. And also, the sun's radiation should not be absorbed by the radiation shield. It should be fully reflected. So they have typically uh, reflective white coatings that are UV resistant, and they have flow patterns such that there is good air circulation. There is no trapped air that will raise the temperature inside. So good air circulation and good radiation reflection and shielding. So that way you're measuring the temperature of the air. Okay. But if a person stood right next to this temperature sensor, he will be feeling much higher temperature than what the sensor is measuring. We will account for the radiation temperature in the radiation temperature term. Okay, so this kind of thermometer, which is actually measuring air temperature, is called a dry bulb thermometer. Okay, dry bulb refers to the fact that the thermometer is not affected by the moisture in the air, and in this sense, it's also not affected by the radiation. Okay, there are other methods. For example, this is a Stevenson shield where you build a well ventilated chamber and you can place any type of thermometers you would like inside it, um, which is also commonly used in meteorological studies. Okay, all right. Now let's look at radiant temperature. It's usually referred to as mean radiant temperature, and it's a critical parameter in estimating thermal comfort of rooms. Um, so the definition is it represents a uniform temperature of an imaginary environment where the radiant heat exchange between an occupant and the surroundings is the same as in the actual environment in which he or she is present. In other words, it's accounting for all the um, radiation sources or sinks in that room. Okay, so how do you measure it? In this case, you don't want the radiation to reflect, you want the radiation to be absorbed. So you have a black body, a globe almost, that picks up radiation from all angles, and the temperature sensor is at the very center. Okay, typically the diameter of this globe is 15 centimeter, and they're usually called globe thermometers. Okay, so they're very commonly used in outside conditions, primarily for measuring the external radiant temperatures. Now, the third parameter, or the third factor, external environment factor that determines thermal comfort, is air velocity. It's a critical factor that helps regulate the body temperature both by directly cooling the surface of the body through convection and also through evaporative cooling when your sweat evaporates. So it's important in these two conditions. In a warm environment, when you feel warm, if you turn on a fan, even though the temperature is not affected much of the air, you feel a little bit colder because of extra heat transfer through both convection and evaporation. Now, we will look into how to read the ASHRAE 55 standard in the next few slides, but this is a typical example of the airspeed versus the operative temperature and the envelope in which somebody would feel comfortable. And I'll tell you what this PMV stands for. It's the predictive mean value, an average value based on tests, empirical tests done on a lot of people. Um, so if it is between minus 0.5 and plus 0.5, that means it is satisfactory for almost 90% of the people. Okay, so what do you need to take away from this is if you look at the absolute low air velocity, the lower limit is 0.1 meter per second for human comfort. So you want some airflow in the room, and the minimum recommended is 0.1 meter per second. Okay, and typically what is the maximum recommended? The maximum recommended is roughly close to 0.8 meter per second in most scenarios. In some scenarios, it could be as low as 0.2 if the room temperatures are really cold, but above 0.8 is only recommended if you have local control of airspeed, right? So if you have a personal fan or desktop fan that you can turn on or off, then you're okay to have higher fan speed. But if the occupant cannot control the airflow and he or she is forced to sit in their room with no control, then they cannot spend a lot of time if the airflow rate is more than 0.8 meter per second. Okay, So that's what this means. The light gray region is where they have no control, and the dark gray is there's no limit on fan speed or airflow if the control is within the person. The understanding here is the person can turn off the fan if they don't feel comfortable, right? So again, this is all coming from ASHRAE 55. Now, how do you measure these fan speeds? So in terms of temperatures, you saw the two different thermometers for radiant and dry bulb temperatures. For air speeds, we have a device called anemometer, and there are several different types of anemometers. This is a common anemometer used for medium flow rates, airflow rates. As you can see, the airflow rate moves or rotates the rotor blades here, and the rotation speed is converted into an airflow speed, and it gives you an average flow through a certain area here. Okay. On the other hand, a hot wire anemometer gives you air velocities at very small points in a very small region. So basically, it has a hot wire. If you zoom in here, you'll see a hot wire, a heated wire, resistance wire, across which air is flowing, and the temperature of this wire is kept constant in most situations. And to keep it constant, you need to send a certain amount of heat, and that depends on the amount of airflow going through. Okay, so based on that, um, the estimation is made on uh, the flow velocities of the air around it. Okay, so it's much more accurate, but it's usually very single point measurement, um, and you will have to uh, measure at multiple locations to find out an average distribution of airflow. All right, so the takeaway from this slide basically is the upper and lower limit in typical situations, which is 0.1 and 0.8 meter per second. Before we jump into the fourth factor, which is humidity, we have to cover a little bit of ground. The first thing we'll cover is understanding of the ASHRAE 55 thermal comfort standard a little bit, and then try to understand how humidity comes into play. The way the standard is written and how the operating recommended operating ranges are described is by combining the three factors that we discussed so far into one. The air temperature, radiant temperature, and the air movement are combined into one single value, okay, and that value is called operative temperature. Okay, it represents a uniform equivalent temperature of an imaginary environment where the occupant would exchange the same amount of heat by radiation and conversion as in the actual environment. So you're combining the radiative temperature along with the dry bulb air temperature to obtain an operative temperature. So when these two are the same, this value is also the same. Okay, if TA is same as TR, then TO is same as TA. Okay, so operative temperature represents an equivalent environment where mean radiative temperature is same as the average air temperature. So that's what that means. So the constant value A here is dependent on the air velocity. Okay, and these are the recommended ranges. All right, now before we go into how to read a operative temperature versus different values in ASHRAE 55 and figure out what is the recommended thermal comfort region within a room, we have to figure out how the ASHRAE 55 standard was developed. Okay, so like I mentioned, it was an empirically developed standard. That means it was done based on a lot of experiments, and the experimental values were obtained by getting votes from test subjects. So there were actual people who were selected and um, placed in carefully controlled climatic chambers where variables like air temperature, radiant temperature, humidity, and air velocity are precisely controlled. Okay, and then the test subjects were asked to report the type of clothing they are wearing, and they are typically asked to sit on a chair so that their metabolic rate is close to 1. But sometimes they are also asked to vary their activity level, a little bit of light walking within the room. Then they were supposed to rate their comfort level based on a temperature scale, okay, a thermal sensation. This is an important point. They were not asked directly whether you're comfortable or not. They were asked whether are you feeling cold, slightly cold, are you feeling cool, are you feeling slightly warm, hot, or are you feeling neutral? So there are 7-point scale and each had a different value, right? Now, they were never asked, are you comfortable or not? The way they figured out whether the people or most people find that room to be comfortable or not was by using an indirect method. First, let's say they asked 100 people, uh, for the sake of the argument. Let's say they asked 100 people. If 100 people provided a score for a certain test condition, and that condition was extremely cold, and all of them put -3, then the predicted mean vote, the mean vote value for that will be -3. If everybody found it to be neutral, then the average will be 0, right? And if everybody found it to be hot, the average will be 3. So the predicted mean value, it's going to take a value between -3 and 3, okay? And if it's 0, that means it's perfect. Everybody finds it acceptable, almost neutral. Um, but you can see sometimes the plus and minus ones could also cancel out. However, this is not directly used. Um, this is further refined by using another variable called the predicted percentage dissatisfied. Okay, so if you get an average value of P and V, predicted mean value, the predicted percentage dissatisfied represent how many percentage of people will find that room not satisfactory. Okay, so lower the number of people that finds it dissatisfactory, the better. The better the condition, the room condition. Okay, now if you look at this formula, it is purposefully created such that the minimum value possible is when the exponent value turns to 1. So then it will be 100 minus 95. This is the minimum value possible. Okay, so lower the PPD, the better. And the lowest it can go, PPD is greater than or equal to 5%. Okay, the lowest it can go is 5%. They're saying you cannot find a room where less than 5% people are not satisfied. That means there's always somebody not satisfied within a room. That's the assumption behind this formula. Okay, and it can take values close to almost close to 100%, where everybody is not satisfied. Okay, so it can take any value um, from 5% to 100%. Now, what does ASHRAE recommend? ASHRAE recommends that PPD should be less than 10%. That means less than 10% of the people should find it not satisfactory. If more people find it not satisfactory, then it's a problem. Now, what is the PME range for which that will happen? You can easily do that. You can do an Excel calculation using this formula. Um, Let me try to get the Excel file. So you can easily do that calculation, and you can see that. So I've put in the formula in here. So minus 3 to 3 PMV, you can see that it almost goes from 100% to a minimum of 5%. And if it is minus 0.5 to 0.5, then you're close to 10%. So this is the range in which ASHRAE says a condition is comfortable for people. The other standard, the European standard, is a little bit more lenient. They say if less than 15% people are satisfied, then the room is thermally comfortable. So that means you get a little bit more wider range of the predicted mean value. So more people can find it a little bit more cold or a little bit more warm. Okay. So this is how the predicted mean value is calculated. And for a given operative temperature versus another variable, uh, the predicted mean value ranges are plotted um, and figured out for um, estimating the best operating conditions for that room. Now, the comfort zone defined by the ASHRAE 55 is a chart that looks somewhat like this. Okay, this is basically a region in which a person would feel comfortable, or the probability with which a person would feel comfortable um, within a range of operating conditions. In this case, it's primarily defined by the operative temperature, which includes both the dry bulb and and the uh, the radiant temperature for still air. And then the other parameter, of course, is the airflow speed. Okay, and it's typically plotted against the parameter which we haven't discussed yet, which is the humidity ratio on the y-axis. It also considers the metabolic rate. In this case, there is one metabolic rate. And in this case, they are also plotting two different clothing um, conditions, 1 CLO and 0.65. So 1 CLO ranges from here to here, 0.65, let's say from here to here. Okay, so you could add other CLO values in here too, but it's this particular graph is showing this. What you can see here is for this conditions of airflow speed and the metabolic rate, it's just recommending a certain temperature range. Um, and the temperature range is changing as the humidity value changes. Okay, and there's a lower and upper limit in temperatures. However, there's no limit, overall limit for humidity. If you look at the humidity here, these are humidity percentages, okay? 20%, 40%, 60%, 80%, and 100%. So the relative humidity percent. So if this line represents 100% humidity line, and we'll understand these things a little bit better once we complete the psychrometric class. So according to the ASHRAE's methodology, where they asked people about whether the room is hot, cold, neutral, basically a sensation of the thermal aspect, there was no limit that could be obtained for humidity. The reason for that is, in my opinion, they didn't ask whether the room was comfortable, okay? Because I know for a fact that if the room is 100% humid, um, most of the temperatures, regardless of the airflow, in most of the temperatures, it would feel really uncomfortable, okay? And if the room is really low in humidity, close to 0%, even then it would be really uncomfortable. So ideally, it would have been great if ASHRAE had a zone that is defined somewhat like this, where there is an upper and a lower limit for humidity too. Unfortunately, their test methodology is I don't want to use harsh words like flawed. Um, let's say it's incomplete in estimating the humidity aspect of thermal comfort. Okay, so um, to understand this further, let's look at an online thermal comfort tool that is provided by the University of Berkeley in California. So if you use this link, you can actually go into this website where you can create that ASHRAE thermal comfort zones by changing any of the parameters, the operative temperature, airspeed, humidity, metabolic rate, clothing level, etc. So if you change the clothing levels, you can see the comfortable zone shifts to one direction. So when I'm reducing the clothing level, I'm saying you're wearing very little clothing, then the comfort zone is more in the warm region. Okay, so you have to be having much warmer temperatures. If you have a lot of clothing, you'll feel more comfortable in colder temperature zones. Okay, and this particular point is the current operative temperature and it's outside the thermal comfort zone. And if it's outside, it would say it does not comply to the standard. If your clothing level is appropriate to the existing temperature, which is the 25-degree operating temperature, it will say it complies with the standard. It calculates a PMV value, calculates a PPD value. Okay. Um, so if the PPD value is less than 10%, it's satisfactory for um, the ASHRAE. So now if you keep changing the clothing value, um, decreasing the clothing value, and the PPD gets about 10%, it's not complying. You can keep changing the other things. For example, if the room is meant for um, another activity, for example, for lifting uh, weight or light machine work, for example, then you need to be a little bit colder, and your clothing level cannot be much warmer clothing, and it will be creating a PPD issue. So you can roughly estimate the temperatures to a certain extent, but it's hard to find an upper and lower limit for humidity. Okay, in most cases you could go to a really high humidity value and you'll be still okay. Okay, so this humidity value is creating a limit for temperature. There is no actual cutoff for humidity itself. Um, in the ASHRAE terminology, you can see 100% humidity is allowed, 0% humidity is allowed, which is not comfortable for human beings at all. Okay. Um, there is also the option of comparing the operative temperature to the airspeeds, which we looked at earlier. So the way you would do that is airspeed versus operative temperature. Okay, so you could do typical seated quiet, low humidity, and no local control. So in that case, you can see the airspeeds are limited between 0.1 meter per second and 0.8 meters per second typically. So that's the typical airflow that you are allowed in that room. There's no there is no local control. Okay. All right. So when you get a chance, try playing with different clothing levels, metabolic activities, metabolic rate levels, humidity controls, um, and keep changing the operative temperatures to see um, whether you're inside or outside the thermal comfort zone. Okay. Now let's look at what are the rough recommended humidity ranges according to different standards. So, like I mentioned, ASHRAE 55 doesn't really recommend a humidity limit, even though in the past, the previous ASHRAE standards several years ago did recommend 30% to 60%, but the latest ones, there are no humidity limits. Okay, the European standard roughly recommends 20 to 70%, and that's recommended by several international standards. The Indian standard recommends 20 to 70%. The Chinese standard recommends an actual moisture content of the air um, to be less than 12 grams per kilogram of dry air. Okay, so the problem with ASHRAE's no humidity limits, and the problem with most standards not able to recommend a humidity zone where the humidity is changing with respect to operative temperature, or the limit is changing with respect to operative temperatures, because of the way of the questionnaire that was given to the people. They were asked for a thermal sensation about comfort. They were not asked about general comfort. The thermal sensation of comfort affected by humidity uh, is different from the general feeling of comfort affected by humidity. Okay, so you might not feel too warm with a high humidity, but you could feel other ways of discomfort with high humidity. You might feel uh, difficulty breathing. You might feel uh, your sweat is not evaporating fast enough. You'll feel sticky. You could feel general discomfort. You would not be able to sleep in such a room, for example. And in terms of low humidity, um, you might feel um, dry eyes, dry skin, dry respiratory tract, drier mucous membranes, which could lead to bleeding from the nose, for example. So typically, such issues also give you a general feeling of not being comfortable, which is not the question that was asked of people. They were asked, "Are you feeling cold or warm?" So there is a fundamental principle um, change that needs to be happening in the way these tests are conducted to be able to generate more meaningful thermal comfort zones with more limits in the top and bottom here rather than going to full 100% and 0% humidity. All right, so having said that, um, it is also very dependent on the culture and the place, the locality of people. So these tests were developed mostly on people in North America and Europe. A test conducted in PSU by Achan Chutakan, who is also teaching this course, had preliminary estimates of um, humidity ranges that are on the higher side, in which Thai people were found to be comfortable, right, 50 to 70%. Um, so, for example, the North America and Europeans find much lower humidities to be comfortable too. So again, this has to be done in a regional basis, country by country, climate patterns, climate zones versus climate zones. All those effects need to be taken care of. Of course, the age of the people and the demographics. And it could be very subjective, and what's recommended in ASHRAE 55 may not be ideal for example, in the Thai situation. Okay, so in general, if you have to go by a number for a max relative humidity in the room, my recommendation is to not go above 70% for any temperature setting in the room. A higher humidity setting in the room could also lead to the growth of mold, dust mites. Um, Generally, the growth of microbes also are favored when you have a high humidity in the room. So trying to keep it below 70% for most of the typical room temperature conditions would be ideal. And if you're dehumidifying the room, try to not go below 30% to reduce the effect of dehydration from your body. Okay, to reduce the chances of mucous membranes getting irritated, the chance of getting cough or other respiratory infections. So keeping it less than, not less than 30% is also recommended. All right, so I hope in this lecture you got a general idea about the factors that affect thermal comfort, both the personal and the environmental factors. All right, thank you.